Elementary number theory and methods of proofs continues with the final section on direct proof and counterexample and the floor and ceiling functions. The floor and ceiling functions of a number are the integers to the immediate left and right of the number, unless the number is an integer, in which case it's floor and ceiling, both are equal to the number itself. Many computer languages have these functions built in. These functions are convenient for writing certain types of computer programs, and they're also important in analyzing the efficiency of many computer algorithms. This you can see on the number line for the floor. The floor of x is n, because x lies between the integer n and n plus 1. The ceiling of a real number x is the number to the right of x on the number line between n and n minus 1, n being an integer. So it's represented by an inequality. The floor and ceiling are both represented by inequalities. N minus 1 is less than x, which is less than or equal to n for the ceiling. Now compute the floor of x and the ceiling of x for each of the following values of x. 25 divided by 4 is what? What would be the floor of that value? That's not an integer. The floor returns an integer. It would be just 6. Yeah, it's an integer value. The ceiling is an integer value also. What would be the ceiling of 25 divided by 4? No, it's the next integer up from the fraction. So since it's 6 point something, it would be 7. So 0.999. What would that be? The floor value? 0, because it's the next integer down. And the next integer up would be the ceiling. That would be 1. Exactly. Now the floor of minus 2.01. The floor. No. -3. It's the next integer down on the number line. And the ceiling would be -2. So here are the worked out solutions and an application. Say there are 1,370 students at a college that are given an opportunity to take buses to an out-of-town event. Each bus holds a maximum of 40 passengers. For reasons of economy, the leader of the event will send only full buses. What's the maximum number of buses the event leader will send? Anybody got a calculator handy? So how many full buses would there be? $34. Now, if they wanted to send all the students, how many would they need? 35. One more than that, because 1370 divided by 40 is 34.25. the floor value being 34, ceiling value being 35. Is the following statement true or false? For all real numbers x and y, the floor of the quantity x plus y equals the floor of x plus the floor of y. Is that true? Why would you say it's no? Oh, on the next page.
You think, because you think it's true.
Yeah, if you find it, you show that it's false by finding a counterexample. Yeah. Mm-hmm. Mm-hmm.
And the floor of that is 4.
Yes.
But then, if we were going to take the floor of reference, right, that would be 1.
Mm-hmm.
Yes. So which would give us 3.
And 4 it does not equal to 3. Exactly. So that is a proof by counterexample that the statement is false. So that is one of the types of proofs that we can do. They use the counterexample of x and y equaling 1/2 and work it out to show that they are in that case not equal. So to arrive at this counterexample, you could have reasoned that x and y are real numbers. Must it necessarily be the case that the equation is true, or could x and y be such that it's not equal? Imagine values that the various quantities could take. For instance, if both x and y are positive, then floor of x and the floor of y are the integer parts of x and y respectively. Little typo there. So x is the fractional part of x plus the floor of x. Y is the floor of y plus the fractional part of y. The fractional part being the part of the number that's to the right of the decimal point. Thus, if x and y are positive, x plus y equals the floor of x plus the floor of y plus the sum of the fractional parts of x and y. But also, x plus y equals the quantity x plus y floored plus the fractional part of x plus y, the quantity x plus y. These equations show that if there exists numbers x and y such that the sum of the fractional parts of x and y is at least 1, or in the case of her example, 1.8, then the counterexample can be found. So that's how you would find a counterexample, or find that a counterexample does exist. Prove that for every real number x and for every integer m, the floor of the quantity x plus m equals the floor of x plus m. Begin by supposing that x is a particular but arbitrarily chosen real number, and that m is a particular integer. You must show that the equation is true, since this is an equation involving the floor of x and the floor of x plus m. It is reasonable to give one of these quantities a name. Let n equals the floor of x. By definition of floor, n is an integer, and n is less than or equal to x and less than n plus 1. This double inequality enables you to compute the value of the quantity x plus m floored in terms of n by adding m to all sides. N plus m equals x plus m, or is less than or equal to x plus m, which is less than n plus m plus 1. Thus, the left-hand side of the equation to be shown is the floor of x plus m equals n plus m. On the other hand, n equals floor of x. The right side of the equation to be shown is the floor of x plus m equals n plus m by substitution. Thus also, the x plus m floored equals the floor of x plus m. So, theorem 4.61. For every real number x and every integer m, this equation is true. Theorem 4.6.2, the floor of n over 2, shows that for any integer n, the floor of n over 2 equals n over 2 if as n is even, and n minus 1 over 2 if n is odd. Given any integer n and any positive integer d, the quotient remainder theorem guarantees the existence of a unique integers q and r such that n equals dq plus r, and r is between 0 and d. The following theorem states that the floor notation can be used to describe q and r as these equations. Q equals the floor of n over d, and r equals n minus d times the floor of n over d. Thus, if on a calculator or in a computer language, floor is built in, but div and mod are not, div and mod can be defined as follows. For a non-negative integer n and a positive integer d. So n div d is the floor of n over d, and n mod d is n minus d times the floor of n over d. Note that d divides n if and only if n mod d equals 0. In floor notation, that means that d divides n if and only if n equals d times the floor of n over d. If an integer, just restating what was already said, this is theorem 4.6.3. N equals dq plus r, and r is less than or equal to, or is greater than or equal to 0 and less than d. Use floor notation to compute 3850 div 17 and 3850 mod 17. So there's that worked out. So you take the floor, the div is just the floor of the division, and the mod is the quantity minus the d times the floor of the above equation, or the above calculation. So it would be 226 for the div and 8 for the mod. Okay. Section 7. We're going to move on away from direct proofs and go to indirect arguments. Contradiction and contraposition. Indirect proofs are more roundabout. One kind of indirect proof, argument by contradiction, is based on the fact that either a statement is true or it is false, but not both. So if you can show that the assumption that a given statement is not true leads logically to a contradiction, impossibility, or absurdity, then that assumption must be false. Hence, the given statement must be true. So this method is also known as reductio ad impossible or reductio ad absurdum, because it relies on reducing a given assumption to an impossibility or absurdity. Method of proof. Suppose that the statement to be proved is false. That is, suppose that the negation of the statement is true. Show that this supposition leads logically to a contradiction, and then conclude that the statement to be proved is true. Use a proof by contradiction to show that there is no greatest integer. For this proof, the certain property is the property of being the greatest integer. So prove that there is no object with this property. Begin by supposing the negation that there is an object with the property. Starting point, suppose there is a greatest integer, call it capital N. This means that capital N is greater than or equal to n for every integer n. Show that this logically leads to a contradiction. Well, if n is the largest integer, n plus 1 is larger than n, and is also an integer because the sum of integers is an integer. So n can't be the greatest integer. So there is no greatest integer. The fact that no integer is both odd and even can also be deduced from the uniqueness part of the quotient remainder theorem. Theorem 472 is there is no integer that is both even and odd. Give an example here. Use the proof by contradiction to show that the sum of any rational number and any irrational number is irrational. So first, you suppose the negation of you want to prove. But be careful of writing this down, because if you make a mistake taking the negation, the entire rest of the proof will be flawed. In this example, the statement to be proved can be written formally as For all real numbers R and S, if R is rational and S is irrational, then R plus S is irrational. The negation of a universal statement is an existential statement. So the negation of the previous statement is there exists a rational number R and an irrational number S such that R plus S is irrational. Is rational. It follows that the starting point and what is to be shown are as follows. Suppose there is a rational number R and an irrational number S such that R plus S is rational. Show that this supposition leads to a contradiction. To derive a contradiction, you need to understand what you are supposing. That there are two numbers, R and S, such that R is rational and S is irrational, and R plus S is rational. By definition of rational and irrational, this means that there are convenient expressions that can be substituted for R and R plus S. But all you can say about S is that it cannot be written as a quotient of integers. So, if you substitute 471 and 472, these two, into the equation, you get A over B plus S equals C over D. Subtract A over B from both sides and gives you this. And then give them common denominators. And then subtract. You are left with this. But B and C, BC minus AD is an integer because multiplication and subtraction of integers is still an integer. And BD is also an integer because multiplication of integers is an integer. So this is a rational number. So S is rational in that, but which contradicts the supposition that S is irrational. It contradicts the primary statement that it is irrational. The sum of any rational number and any irrational number is irrational by theorem 473. Argument by contraposition. A second form of indirect argument by contraposition, is based on the logical equivalence between a statement and its contrapositive. To prove a statement by contraposition, you take the contrapositive of the statement, prove the contrapositive by direct proof, and conclude that the original statement is true. So you express the statement in the form, to be proved in the form, for all x in D, if P of x, then Q of x. Rewrite it in the contrapositive form, for all x in D, if Q of x is false, then P of x is false. Now prove the contrapositive by direct proof. Suppose x is a particular but arbitrarily chosen element of D such that Q of x is false. Show that P of x is also false. Now the slide's kind of screwed up here, but prove that for every integer n, if n squared is even, then n is even. First, form the contrapositive of the statement to be proved. For every integer n, if n is not even, then n squared is not even. By the quotient remainder theorem, with divisor equal to 2, any integer is either even or odd. By theorem 472, no integer is both even and odd. So if an integer is not even, then it is odd. Thus, the contrapositive can be restated as, for every integer n, if n is odd, then n squared is odd. Relation between proof by contradiction and proof by contraposition. Well, any proof by contraposition can be recast in the language of proof by contradiction. In a proof by contraposition statement, for all of x and d, if p then q is proved by giving a direct proof of the equivalent statement for all x and d. If not q, then not p. To do this, you suppose you are given an arbitrary element of d, x of d, such that not q of x is true. You then show that not p is true through a sequence of steps. To rewrite the proof as a proof by contradiction, you suppose that there is an x and d such that p of x and not q of x. You then follow steps to the steps of the proof by contraposition to deduce the statement not p of x. But not p of x is a contradiction to the supposition that p of x and not q of x. Because to contradict a conjunction of two statements, it is only necessary to contradict one of them. So, proof by contradiction, you suppose there exists an element in D such that P of X and not Q of X. Contradiction, you show that P of X and not P of X is the case. For every integer, so continue with the proposition there. Proof as a problem-solving tool. Well, direct proof, disproof by counterexample, proof by contradiction, and proof by contraposition are all tools that may be used to help determine whether statements are true or false. Working with examples might have given you a sense that a statement of the form, for all elements in a domain, if the hypothesis is true, then the conclusion is true, might be true. To explore further, imagine elements in the domain that satisfy the hypothesis. Ask yourself, must they satisfy the conclusion? If you can see that the answer is yes in all cases, then the statement is true and your insight will form a basis for a direct proof. If after some thought it is not clear that the answer is yes, ask yourself whether there are elements of the domain that satisfy the hypothesis and not the conclusion. If you are successful in finding some, then the statement is false and you have a counterexample. On the other hand, if you find you're not successful finding such elements, perhaps none exist. Perhaps you can show that assuming the existence of elements in the domain that satisfy the hypothesis and not the conclusion leads logically to a contradiction. If so, then you have given the statement is true. If so, then the given statement is true, and you have the basis for a proof by contradiction. Alternatively, you could imagine elements of the domain for which the conclusion is false and ask whether such elements also fail to satisfy the hypothesis. If the answer in all cases is yes, then you have the basis for a proof by contraposition. That is how you approach determining what method of proof you use to you use to prove a particular statement. You start with the most direct approach, the direct proof. If that doesn't work, maybe you can find a counterexample to show that it's false. And if you don't, if you can't find any counterexamples, try the contradiction, proof by contradiction. And then if that doesn't work, try contraposition. Now, section 8 continues the indirect argument with two famous theorems. Mathematicians believed at one time that given any two line segments, a certain unit of length could be found so that segment A was exactly m units long and segment B was exactly n units long for some integers m and n. The segments were said to be commensurable with respect to the special unit of length. Then the ratio of the lengths of A and B would be in the same proportion as the ratio of the integers m and n, symbolically represented here. Now it is easy to find a line segment of square root of 2, the length of square root of 2, take the diagonal of a unit square, and by the Pythagorean theorem, you know that c equals to the square root of 2. So if the belief of the ancient Greeks were correct, there would be integers m and n such that the diagonal over the side would be integers. This would imply that c equals square root of 2 equals m over n. But then square root of 2 would be a ratio of two integers, or in other words, square root of 2 would be rational. But square root of 2 is in fact irrational. So what the Greeks thought was not true. Proof by contradiction that 1 plus 3 times the square root of 2 is irrational. The essence of the argument is the observation that if 1 plus 3 times the square root of 2 could be written as a ratio of integers, then so could the square root of 2. But by theorem 481, we know that to be impossible. So therefore, 1 plus 3 times the square root of 2 is irrational. Are there infinitely many prime numbers? You know that a prime number is a positive integer that cannot be factored as a product of two smaller positive integers. Is the set of all such numbers infinite, or is there a largest prime number? The answer was known to Euclid, and a proof that the set of all prime numbers is infinite. Euclid's proof requires one additional fact that we have not yet established. If a prime number divides an integer, then it does not divide the next successive integer. So if for any integer a, any prime number p, if p divides a, then p does not divide a plus 1. And from there you can derive that the set of prime numbers is infinite. When to use indirect proof? Well, the examples in this section have not provided a definitive answer to the question of when to prove a statement directly or when to prove it indirectly. Many theorems can be proven either way. If given the choice, if both options are available, the direct proof is typically clearer and less clumsy. So I would choose that over the indirect proof. In the absence of obvious clues suggesting the indirect argument, try to first prove a statement directly. Then if that does not succeed, look for a counterexample. If the search for a counterexample is unsuccessful, look for a proof by contradiction or contraposition. So that'll be about it for the day. Midterm next Thursday. Chapters 3 and 4 at least, maybe some from 1 and 2. But midterm grades are due into the registrar's office on the following Monday, so you need to be here for that exam next Thursday, the 6th. So see you next week on Tuesday. We'll finish up chapter 4. Don't forget the homework that I gave out last Tuesday. Have a good day.